In this lecture, we will be learning about how air pollution can affect human health and the environment. The effects can be significant. Even an increase of 10 micrograms of particulate matter per cubic meter of air can decrease life expectancy by 10 years. Here are the learning objectives for this chapter. By the end of this chapter, you should be able to answer the following questions. What are the main types and sources that we term conventional pollutants? We also call these criteria pollutants. Describe some hazardous air pollutants and their effects on humans and the environment. Understand the difference between point source and non-point source emissions and differentiate between primary and secondary pollutants. Londoners had been accustomed to filthy air since the beginning of the Industrial Revolution, but over a period of 4 days in 1852, days that they experienced the worst air pollution disaster on record. Smoke, soot, and acidic droplets of fog made the air opaque. Thousands died, thousands more became ill, and our view of air pollution changed forever. In early December 1952, a dense blanket of coal smoke and fog settled on the city. Under normal conditions, winds keep polluted air moving away from the city and out over the countryside. But from time to time, an inversion develops. As the name implies, an inversion occurs when layers of air are out of order. Still, cold air settles near the ground, trapped by warmer layers above. The killer smog of 1952 came on suddenly on Friday, December 5th. Home heaters and industrial furnaces were working in full force, pumping out smoke on the cold winter day. During the afternoon, visibility plummeted and traffic came to a halt as drivers were blinded by the smoke and fog. Hundreds of cattle at a cattle market were the first to go. With lungs blackened by soot, they suffocated while standing in their pens. People could cover their faces and go indoors, but the soot soon reached inside buildings as well. The ill and elderly, especially those with lung or heart ailments and heavy smokers, were the next to go. Hospitals filled with victims of bronchitis, pneumonia, lung inflammations, and heart failure. Like the cattle in the market, victims' lungs were clogged by smoke and microscopic soot particles. Their lips turned blue and they asphyxiated due to lack of oxygen. 4 days later, a change in weather brought fresh winds into London and the inversion dissipated. Studies showed that at least 4,700 deaths were attributable to this air pollution. These alarming death counts caught the attention of politicians and the public alike and gradually led to changes in expectations and practices. In this chapter, we'll examine major types and sources of air pollutants. We'll also consider policies and technology that help ensure that events like the smog of London doesn't happen in your town. This comment by the International Energy Agency in 2010 is in reference to the emissions of carbon dioxide and its effects on climate change. Because of recent political developments in the United States, the likelihood of having peak emissions by 2020 is bleak and will certainly not happen in the United States from government intervention. However, because of the quickly dropping costs of solar and wind energy, the expense of coal mining, and the fairly inexpensive natural gas, which burns more cleanly, we are generally moving in the right direction. Clean air is something we take for granted when we have it, but once a region's air pollution becomes severe, removing those pollutants presents an enormous challenge. Pollution comes in many forms: smoke, haze, dust, odors, corrosive gases, noise, and toxic compounds are among our worst widespread pollutants. Some pollutants, such as sulfur dioxide, irritate our eyes and lungs. Fine particulates penetrate deep into our lungs. Airborne metals enter our bloodstream when we breathe them and then damage nerves and brain function. Worldwide, these air pollution emissions add up to about 2 billion metric tons per year. Sometimes, the health and environmental costs of air pollution are shocking, as in London in 1952, but most of the time the costs are more subtle. Chronic illness, resulting from low-level ongoing exposure is likely to cause more deaths and higher healthcare costs than serious but infrequent deadly smog events. The Organization for Economic Cooperation and Development has projected that by 2050, chronic exposure to ground-level ozone, fine particulate matter, sulfur dioxide, and other pollutants will cause 3.6 million premature deaths every year. While air quality is improving in many industrialized countries, newly developing countries have growing pollution problems. Xi'an, China often has particulate levels above 300 micrograms per cubic meter. Of the 20 smoggiest cities in the world, 16 are in China. China's city dwellers are 4 to 6 times more likely than rural people to die of lung cancer. As we noted earlier, of the 20 most polluted cities in the world, China is home to 16 of them, and Beijing often exceeds, by many times, the acceptable air standards set by the United States Environmental Protection Agency. Amendments to the Clean Air Act in 1970 designated new standards to be applied equally across the country for 6 major pollutants: sulfur dioxide, nitrogen oxides, carbon monoxide, ozone and its precursor volatile organic compounds, lead, and particulate matter. These 6 are referred to as conventional or criteria pollutants, and they were addressed first because they contributed the largest volume of air quality degradation and also are considered the most serious threat to human health and welfare. Transportation and power plants are the dominant sources of most criteria pollutants. National ambient air quality standards designated allowable levels for these pollutants in the ambient air, that is, the air around us. The slide shows the anthropogenic or man-made sources of 6 primary air pollutants in the United States. These sources are evenly divided between power generation, transportation, agriculture, construction, and miscellaneous sources. The main source of lead in the environment are transportation, which results from the burning of gasoline and smelting and processing. The primary source of nitrogen oxides are power plants, which burn fossil fuels, as well as transportation, which also burns fossil fuels. Carbon monoxide is also primarily a transportation-related pollutant. Transportation also plays a role in the formation of volatile organic compounds. Other sources of VOCs are solvents and waste disposal. Power plants and industrial emissions are the major source of sulfur dioxide in the environment. And both sulfur dioxide and nitrogen oxides are formed by the combustion of fossil fuels in power production. In addition to the 6 conventional pollutants, the Clean Air Act regulates an array of unconventional pollutants, compounds that are produced in less volume than conventional pollutants, but that are especially toxic or hazardous, such as asbestos, benzene, mercury, polychlorinated biphenyls, and vinyl chloride. Most of these are uncommon in nature or have no natural sources. EPA determined in 2009 that emissions of carbon dioxide and other long-lived greenhouse gases that build up in the atmosphere endanger the health and future generations by causing climate change and ocean acidification. Long-lived greenhouse gases, which trap heat in the atmosphere, include carbon dioxide, methane, nitrous oxide, and fluorinated gases. These gases are produced by a numerous and diverse array of human activities. The addition of carbon dioxide to the list of regulated pollutants has been politically controversial. In May 2010, the National Research Council, an operating arm of the National Academy of Sciences, published an assessment which concluded that climate change is occurring, is largely caused by human activities, and poses significant risks for, and in many cases is already affecting, a broad range of human and natural systems. The United States Environmental Protection Agency began regulating greenhouse gases under the Clean Air Act from mobile and stationary sources of air pollution for the first time on January 2nd, 2011. Standards for mobile sources have been established pursuant to Section 202 of the Clean Air Act, and greenhouse gases from stationary sources are controlled under the authority of Part C of Title I of the Act. The basis for regulations was upheld in the United States Court of Appeals for the District of Columbia in 2012. Many pollutants come from a point source, such as a smokestack. Fugitive or non-point source emissions are those that do not go through a smokestack. Leaking valves and pipe joints contribute as much as 90% of the hydrocarbons and volatile organic chemicals emitted from oil refineries and chemical plants, and increasingly from natural gas wells. Dust, as from mining, agriculture, and building construction and demolition, is also considered a fugitive emission. Primary pollutants are substances that are harmful when released. Secondary pollutants, by contrast, become harmful after they react with other gases or substances in the air. As shown in this photograph, many of our most serious pollutants are fugitive emissions from petrochemical facilities such as this one in Baton Rouge, Louisiana. Now let's look at the conventional pollutants in more detail. Sulfur dioxide is a colorless, corrosive gas that damages both plants and animals. Once in the atmosphere, it can be further oxidized to sulfur trioxide, which reacts with water vapor or dissolves in water droplets to form sulfuric acid, a major component of acid rain. Sulfur dioxide and sulfate ions damage health. Sulfate particles and droplets also reduce visibility in the United States by as much as 80%. Minute droplets of sulfuric acid can penetrate deep into lungs, causing permanent damage, as well as irritating eyes and corroding buildings. In plants, sulfur dioxide destroys chlorophyll, eventually killing tissues. Sulfur dioxide from coal smoke, along with particulate matter, was a principal component of London's deadly smog event of 1952. Sulfur dioxide concentrations and deaths during the London smog of December 1952 are shown here. The EPA standard limit is 0.08 milligrams per cubic meter, dashed line A. The soybean leaf at right was exposed to 2.1 milligrams per cubic meter of sulfur dioxide for 24 hours. White patches show where chlorophyll has been destroyed. Because plants depend on chlorophyll for energy and food production, acid deposition can quickly kill and damage plant species. Nitrogen oxides are highly reactive gases formed when the heat of combustion initiates reactions between atmospheric nitrogen, N2, and oxygen. The initial product, nitric oxide, oxidizes further in the atmosphere to nitrogen dioxide, a reddish-brown gas that gives photochemical smog its distinctive color. Because these gases convert readily from one form to the other, the general term NOx, with X indicating an unspecified number of oxygen atoms, is used to describe these gases. Nitrogen oxides combine with water to form nitric acid, which is also a major component of acid precipitation. Excess nitrogen in water is also causing eutrophication of inland waters and coastal seas. Carbon monoxide is less common but more dangerous than the principal form of atmospheric carbon, carbon dioxide. Carbon monoxide is a colorless, odorless, but highly toxic gas produced mainly by incomplete combustion of fuel, like coal, oil, charcoal, wood, or gas. CO, carbon monoxide, inhibits respiration in animals by binding irreversibly to hemoglobin in blood. In the United States, 2/3 of the carbon monoxide emissions are created by internal combustion engines in transportation. Land clearing, fires, and cooking fires also are major sources. About 90% of the carbon monoxide in the air is consumed in photochemical reactions that produce ozone. Ozone is important in the upper atmosphere, where it shields us against ultraviolet radiation from the sun. But at the ground level, ozone is a highly reactive oxidizing agent that damages eyes, lungs, and plant tissues, as well as paint, rubber, and plastics. Ground-level ozone is a secondary pollutant created by chemical reactions that are initiated by solar energy. In general, Pollutants created by these light-initiated reactions are known as photochemical oxidants, that is, oxidizing agents that irritate tissues and damage materials. One of the most important of these reactions involves formation of single atoms of oxygen by splitting nitrogen dioxide. This atomic oxygen then binds to a molecule of diatomic oxygen to make ozone or triatomic oxygen. The acrid, biting odor of ozone is a distinctive characteristic of photochemical smog. The heat of fuel combustion causes nitrogen oxides to form from atmospheric nitrogen and oxygen. Nitrogen dioxide interacts with water to form nitric acid, a component of acid rain. In addition, solar radiation can force nitrogen dioxide to release a free oxygen atom, which joins to atmospheric or diatomic oxygen, creating ozone or triatomic oxygen. Fuel combustion also produces incompletely burned hydrocarbons, including volatile organic compounds. Both ozone and volatile organic compounds contribute to photochemical oxidants in reactions activated by sunlight. The VOC shown here is benzene, a ring of 6 carbon atoms with a hydrogen atom attached to each carbon. Interacting with ozone to produce smog are a variety of volatile organic compounds, or VOCs, that contribute to the formation of ozone and other photochemical oxidants. A wide array of these organic, volatile chemicals derived from industrial processes such as refining of oil and gas or plastics and chemical manufacturing. The main concerns are the more dangerous synthetic organic chemicals such as benzene, toluene, formaldehyde, vinyl chloride, phenols, chloroform, and trichloroethylene, which are released by human activities. Principal sources are incompletely burned fuels from vehicles, power plants, chemical plants, and petroleum refiners. Lead, our most abundantly produced metal air pollutant, impairs nerve and brain functions. It does this by binding to essential enzymes and cellular components and disabling them. A wide range of industrial and mining processes produce lead, especially smelting of metal ores, mining, and burning of coal and municipal waste, in which lead is a trace element, and burning of gasoline to which lead has been added. Historically, leaded gasoline was the main source of lead in the United States, but leaded gas was phased out in the 1980s. Since 1986, when the ban was enforced, children's average blood lead levels have dropped 90%, and average IQs have risen 3 points. Banning leaded gasoline in the United States was one of the most successful pollution control measures in American history. Now, 50 nations have renounced leaded gasoline. The global economic benefit of this step is estimated to be more than $200 billion per year. Particulate material includes dust, ash, soot, lint, smoke, pollen, spores, algal cells, and many other suspended materials. Aerosols, or extremely minute particles or liquid droplets suspended in the air, are included in this class. Particulates often are the most apparent form of air pollution, since they reduce visibility and leave dirty deposits on windows, painted surfaces, and textiles. Breathable particles smaller than 2.5 micrometers are among the most dangerous of this group because they can damage lung tissue. Asbestos fibers and cigarette smoke are among the most dangerous respirable particles in urban and indoor air because they are carcinogenic. Certain chemicals are regulated by the EPA as hazardous air pollutants because of their ability to cause cancer, nerve damage, persist for long periods in the environment, and to bioaccumulate. Let's take a look at some of these important chemicals. So a special category of toxins is monitored by the US EPA because they are particularly dangerous, called hazardous air pollutants, or HAPS. These chemicals cause cancer, nerve damage, disrupt hormone function, and fetal development. These persistent substances remain in ecosystems for long periods of time and accumulate in animal and human tissues. Most of these chemicals are either metal compounds, chlorinated hydrocarbons, or volatile organic compounds. Gasoline vapors, solvents, and components of plastics are all HAPS that you may encounter on a daily basis. Many HAPs are emitted by chemical processing factories that produce gasoline, plastics, solvents, pharmaceuticals, and other organic compounds. Benzene, toluene, xylene, and other volatile organic compounds are among these. Dioxins, carbon-based compounds containing chlorine, are released mainly by burning plastics and medical waste containing chlorine. The EPA reports that 100 million Americans, one-third of us, live in areas where the cancer rate from HAPS is 10 times the normally accepted standard for action, which is 1 in 1 million. Benzene, formaldehyde, acetaldehyde, and 1,3-butadiene are responsible for most of this HAP cancer risk. To help inform communities about toxic substances produced and handled in their area, Congress established the Toxic Release Inventory, or TRI, in 1996. This inventory collects self-reported statistics from 23,000 factories, refineries, hard rock mines, power plants, and chemical manufacturers to report on toxic releases above certain minimum amounts and waste management methods for 667 toxic chemicals. Although this total is less than 1% of all chemicals registered for use and represents a limited range of sources, the TRI is widely considered the most comprehensive source of information about toxic pollution in the United States. The law grew out of concerns surrounding Union Carbide's release of toxic gases in the 1984 Bhopal disaster and a smaller 1985 release in Institute, West Virginia. The inventory was first proposed in the 1985 New York Times op-ed piece written by David Sarakin and Warren Muir, researchers for an environmental group, INFORM. Congress established TRI under the Emergency Planning and Community Right to Know Act of 1986 and later expanded it in the Pollution Prevention Act of 1980. A variety of hazardous emissions from some 23,000 facilities in the U.S. are monitored by the Toxic Release Inventory. The Toxic Release Inventory is a publicly available database containing information on toxic chemical releases and other waste management activities in the United States. The database is available from the United States Environmental Protection Agency and contains information reported annually by some industry groups as well as federal facilities. Each year, companies across a wide range of industries, including chemical, mining, paper, oil, and gas industries that produce more than 25,000 pounds or handle more than 10,000 pounds of a listed toxic chemical, must report it to the TRI. The TRI threshold is initially set at 75,000 pounds annually. If the company treats, recycles, disposes, or releases more than 500 pounds of that chemical into the environment as opposed to just handling it, then they must provide a detailed inventory of that chemical. Airborne metals originate mainly from combustion of fuel, and especially coal, which contains traces of mercury, arsenic, cadmium, and other metals, as well as sulfur and other trace elements. Airborne mercury has received special attention because it is a widespread and persistent neurotoxin, a substance that damages the brain and nervous system. Minor doses can cause nerve damage and impairments, especially in young children and developing fetuses. So some 70% of airborne mercury is released by coal-burning power plants. Metal ore smelting and waste combustion also produce airborne mercury and other metals. About 75% of human exposure to mercury comes from eating fish. This is because aquatic bacteria are mainly responsible for converting airborne mercury into methyl mercury, a form that accumulates in living animal tissues. Canned tuna is our dominant source of mercury because it is a top predator fish that we eat in abundance. The primary source of mercury in seafood is from release of mercury from coal combustion. We have spent a considerable amount of effort and money to control the major outdoor air pollutants, but we have only recently become aware of the dangers of indoor air pollutants. The US EPA has found that indoor concentrations of toxic air pollutants are often higher than outdoors. Because people generally spend more time inside than out, they are exposed to higher doses of these pollutants. In some cases, it would be illegal outside or in the workplace. Under some circumstances, compounds such as chloroform, benzene, and styrene can be 70 times higher in indoor air than in outdoor air. Molds, pathogens, and other biohazards also represent serious indoor pollutants. In this lecture, we have learned about a class of air pollutants called conventional pollutants or criteria pollutants. These consist of lead, carbon monoxide, particulate matter, nitrogen oxides, sulfur oxides, and volatile organic compounds that lead to ozone. The 6 were regulated because they were produced in great volume and have known health effects. The other class of regulated air pollutants are the hazardous air pollutants, or HAPS, that are present in lower volumes but are particularly toxic or damaging to the environment. In this lecture, we also learned about point sources and non-point sources. Point sources are those which are emitted from an identifiable location, such as a smokestack. Non-point sources, which are sometimes called fugitive emissions, are not emitted from a single identifiable location. Primary pollutants are those which are toxic when they are released to the environment. Secondary pollutants are those which become toxic after reactions that occur after they are released. Federal laws, like the TRI and Community Right to Know, passed as a result of the Union Carbide accident, help keep public informed about possible hazards, and mercury remains a significant air pollutant. The primary source of mercury in the environment is from the combustion of coal and coal-powered electric generation facilities. In the next lecture, we will be looking at the ways that air pollution can impact the climate.